intermolecular forces. Okay, so intermolecular forces are forces between molecules. Okay, forces between molecules. Okay, they are not bonds. A bond is between atoms. Bonds are between atoms, forces are between the whole molecules. Right? We're going to see an example of that. Now there are 3 intermolecular forces between the molecules. 3 intermolecular forces. Okay, there is the first one is called induced dipole to dipole interactions. Induced dipole to dipole, also known as London forces. The second type we're going to talk about is the permanent dipole to dipole interactions. Interactions. And the third type of intermolecular force is hydrogen bonds. Hydrogen bonds. Now, even though it uses the term bond, it is not a bond. Bonds are between atoms. This is a force. Okay, these are the 3 forces, and they increase in strength. Okay, this is the strongest intermolecular force. Strongest intermolecular force. And the induced is the weakest. But saying that the hydrogen bonds are the strongest intermolecular force, they're still a lot weaker than a covalent bond. They're approximately 1/10 the strength of a covalent bond, approximately. So they're still very weak. Okay, but it's the strongest of the 3. So you need to know what each one is. So now between all molecules, we're going to do induced. We're going to do first. We're going to do induced dipole to dipole intermolecular force. Okay, interactions. Now this is between all molecules. These forces exist between all molecules, right? And it's all to do with electrons. If we take, this can be a molecule. If you take a molecule and there's lots of electrons in the molecule, then the electrons are moving around the whole time. They're not stationary. They're moving around the whole time. And in one instant, in 1 second, there may be more electrons on one side of the molecule than the other. So we put a slightly negative charge on one side of the molecule, because electrons are moving around, and for 1 instant, for 1 second, there might be more electrons on one side of the molecule than the other. The way to think about it is like if you think about in your classroom and all the students in your classroom, and if all the students in your classroom, they're the electrons, and the classroom is the molecule, and all the electrons, all the students get up and walk around the classroom at the same time. Just for an instant, there may be more electrons on one side of the room, on one side of the molecule than the other. And it generates a temporary dipole. So it'll be slightly negative, whereas the other side will be slightly positive. Okay, so we call it an instantaneous dipole. Be careful with your spelling here. Instantaneous dipole, or temporary dipole. It's just a temporary dipole. Okay, now once it's happened in one molecule, okay, as soon as that's happened in the neighboring molecule, all the electrons in this molecule will repel and run to the other end of the molecule. So it creates a dipole in the next molecule, which creates a dipole in the next molecule, and so on, so on. Okay, and the word that we use for this create is we use the word induces. Okay, so the instantaneous dipole, induces, which just means creates or creates a dipole in the neighboring or the next molecule. In the neighboring molecule. Okay, and this carries on, but then it disappears because the electrons are moving the whole time. So it happens and then it disappears. Okay, now this depends on the number of electrons. The more electrons, the greater the effect. Yeah, the greater the induced dipole. Okay, the larger, the greater the induced dipole. So therefore, more energy will be needed to separate. Okay, so let's have a look at an example. Okay, so a classic example of this is when you look at group 7. And you look at group 7 and you take chlorine, bromine molecule, iodine. Remember that they are diatomic molecules. They go around in twos. Okay, now they have not Van der Waals forces, instantaneous dipole to dipole forces between the molecules. Okay, this is a gas at room temperature, this is a liquid at room temperature, this is a solid at room temperature. So this has got the lower melting point and this has got the higher melting point. And the reason is because iodine is the largest of these three molecules. Iodine is the largest molecule, has the most electrons, and therefore has the larger, the greater induced dipole to dipole interactions. And therefore more energy will be needed to separate the molecules. Remember that when you melt something or when you boil it, you are not breaking the bonds. So if you take iodine, for example, there is a covalent bond inside the molecule. But when you want to melt it or boil it, then you are breaking the forces between the molecules, not the bonds inside the molecules. Okay, now these forces, these London forces, these induced dipole to dipole forces, they used to be called Van der Waals forces. Okay, but the term has now changed. So they used to be called Van der Waals. If you're doing any of the old exam papers, they are called Van der Waals forces, but now the term has changed and it's called induced dipole to dipole or London forces. So the name has changed, but they're actually the same thing. Okay, that's the weakest intermolecular force. Okay, then number two is the permanent dipole to dipole, which is like the middle force. There's the weakest, that's the strongest, and this is the middle one. Okay, so permanent dipole to dipole forces. Permanent dipole to dipole forces. So this is when as it says, the dipole is permanently there. Classic example, HCl. If you take HCl, you have a permanent dipole because chlorine is electronegative. So it's not a temporary, it's not an instantaneous, it's always there. And if you take another HCl molecule, slightly positive, slightly negative. There is an attraction between the slightly negative atom on one molecule and a slightly positive, and that is called a permanent dipole-to-dipole interaction. That is called a permanent dipole-to-dipole interaction, and that is stronger than not van der Waals forces, stronger than the induced dipole-to-dipole interactions because it is permanently there. Okay, the last intermolecular force and the strongest intermolecular force is hydrogen bonds. It's not a bond, even though it's got bond in the title. Okay, so hydrogen bonds. So hydrogen bonds, clean piece of paper. Hydrogen bonds. Okay, now, hydrogen bonds. Right, so we just did about electronegativity. The four most electronegative atoms, are FONCL: fluorine, oxygen, nitrogen, chlorine. Okay, they are the four, and it's a really good way to remember it. Just go FONCL. Right, but chlorine is not electronegative enough to do hydrogen bonding. Okay, these are the only three that are electronegative enough. I'm just going to write electroneg to form hydrogen bonds. And in order to have hydrogen bonds, you need either fluorine or oxygen or nitrogen joined to a hydrogen atom. Okay, has to be joined to a hydrogen atom. Right, so let's give an example. So let's do water. Water is a really good example, right? So you've got water, non-linear, negative, slightly negative, electronegative oxygen atom. It's a polar molecule, okay? And if you take another water molecule, there's a covalent bond inside the molecule, slightly negative, slightly positive, okay? The hydrogen bond is between the lone pair on the electronegative, between the lone pair and the hydrogen. That is a hydrogen bond. Can you see when I'm drawing this as well? I don't draw it as a single line, because that's a covalent bond. You can't do that because it's a covalent bond. You've got to do it as a dashed line like that. Okay, that's a hydrogen bond, and the slightly positive hydrogen just kind of nestles, gets tucked between the two oxygen atoms. All right, but if you have, for example, if you take a, let's think of an example. Let's take this, okay, this chemical here. This chemical here, does anybody know what this chemical is called? So this is propanone. It's a ketone. So I said to have hydrogen bonding, you had to have an electronegative atom. Well, it does. It has an electronegative atom. But the electronegative atom has to be joined to a hydrogen atom. The electronegative atom is not joined to a hydrogen atom. So between the molecules of propanone, there is not hydrogen bonding. Instead, we have a permanent dipole, because oxygen is electronegative, a permanent dipole, and it is the permanent dipole to dipole interactions, because you've got permanent dipole there.